Hello, in this video, we'll be discussing integrated circuits, sometimes called ICs, ICCs, or microchips. They're the cornerstone of all modern electronics as they put entire circuits into a single package. We'll be discussing their history, types of chips, even specific models, and the importance of families and other designations. So, what exactly is an integrated circuit? Most people know it better by the term microchip, which was first popularized in the 1960s. It's an entire circuit fabricated as one piece and that includes the components, with anywhere from thousands to billions of microscopic components. It reduced big circuits into small packages, often the size of a postage stamp, but there were certainly bigger models. The 5400 series became the first widely available ICs. I believe they came out in 1964. And then 2 years later, the 7400 series came out for commercial applications. Both of them are still in wide production, although some of the materials and methods for their production has been updated through the years. The price of an IC can wildly vary from pennies to hundreds of dollars, depending on the chip, because we're talking about a lot of different components. An IC is mostly made of silicon, where impurities are introduced to draw individual components in extremely tiny patterns. If you've ever bought a hobby kit, perhaps one with something like an Arduino or an ESP32, you probably have at least one in your collection, not including the microcontroller. Often it's a 595 shift register, but it might be other chips as well. This can all be very overwhelming, but good news, every IC, much like pretty much every other component, has a complex data sheet giving users and buyers all the information they'll probably need about the chip. The history of the IC started with the invention of the first transistor in 1947, and without that, ICs wouldn't be possible. The concept of the IC was first proposed by Jeffrey Dahmer in 1952, and then 6 years later, in 1958, Jack Kirby built the first working IC. A year later, in 59, Robert Noyce built the first practical monolithic IC, which made ICs both compact and portable and practical. The year after that, in 1960, the MOSFET was invented, which made microscopic transistors possible. Fairchild came out with the micro logic line that became the first mass-produced IC series. And then IC started to really ramp up production to meet the U.S. missile program, the Minuteman missile program, and the Apollo guidance computer because they both needed large numbers. In 1964, the 5400 series came out to military specification. A year later, Moore's Law came out, which a lot of people, anybody who's gotten to anything to computers is familiar with Moore's Law, that the number of transistors on a microchip doubles roughly every 2 years, while the cost of computers is cut in half. And then in 66, the 74 series came out, commercial specifications, which were cheaper to the 5400. And then 1971, 3 years after Intel was founded, the first microprocessor came out. That's the Intel 4004 or 4040, whatever. It was also in the 1970s that lower power and Schottky IC families became popular because they provided lower power consumption. In the 80s, the CMOS families got popularized, and then the 1910s, FinFETs started replacing MOSFETs for CPUs. 2020s, GAFETs have been starting to replace FinFETs. Now, here's a few pictures of some ICs. You got a double pin analog IC, got surface mount chips, system on a chip, etc. Now, one thing that a lot of people don't realize with an integrated circuit, most of that chip is actually not the chip itself. It's the housing and it's the wires, the pins that connect everything. The actual die, the actual chip is could maybe fit on the tip of your little finger, even if the chip is much bigger. And if you zoom in on a chip die, this is actually what you'll see. It's a virtual little city of components. And actually, this is probably just still in the thousands. I'm not really sure which chip this is. Just to give you an idea of scale, in this case, you've got some surface mount ones, and then I believe, no, actually, that's surface mount as well. I think these are all surface mounted chips. But this is in inches here, so they can get really tiny. Now, here are some of the IC packages. Keep in mind, most of these are surface mount, and then some are through hole. The ones we'll be focusing on the most are dual inline packages called dips, and then there's P-dips, which are just dips using a cheaper plastic body as opposed to ceramic or something else. Surface mount ones attached to pads, and you can make them pretty tiny through holes. They still have to be big enough to actually put the pins through. But a lot, as I said, most of these are pretty much surface mount in some variety or another, and we'll just be focusing really on dips at this point. Now, there's a good number of considerations when selecting an IC. The most obvious is its operation and possible application. A 555 timer and a 595 shift register do completely different things, so they're not interchangeable. Price might be a consideration. You might look at a couple of ICs depending on what your intended application is, and in that case, the price may actually vary. The operating voltages, there's going to be ranges for both digital and analog. If digital, can it work with 3.3 or is it stuck on 5 volts? Or even something like 1.8. Current limits, as well as we've discussed before, too much excess current can destroy the chip. Temperature ratings, probably not a huge consideration because most of your projects are going to be at room temperature, but if they're not, you might look into it. The speeds inside the chip measured in hertz, package outline, which we've already just mentioned, ESD ratings. I'm sure you heard of touching electronic and then electro shock from your finger, electrostatic from your fingers destroys it. That's probably not as much of a consideration these days as they've made chips a little more hardy, as it were. But if you've got a really expensive chip, then don't take the chance. If you're working with breadboards, is it friendly to breadboards? Which again is a broader question than just the outline. And can it work off signals from a development board if you need it for your application, such as a Pi, Arduino, ESP32? All good questions. All right, let's look at every circuit and what kind of ICs it has available, which aren't many, but that's fine. Let's see, going down the list here, we've got logic gates, although that's not implemented as an IC. We've got latches, which again, this could also be put in IC as well. And here's our integrated circuits. We've got a binary to 7 segment driver here. This is a very generic one, uh, although you see some of those things on actual chips. We've got a counter chip. We've got a 5.5 timer. So this is specific chip that actually exists. And then we've got analog to digital, digital to analog, and that's pretty much our only options for every circuit. All right, now in Falstad, we actually have some other options because we can make sub-circuits and essentially build our own ICs. But let's see what we have naturally. Analogs, we've got a couple of different things. 5.5 timer, phase comparator, and we've got our digital analog stuff and VCOs, monostable. These are, again, they're generic models, but you can find chips that are this plus more. Digital tips, we've got flip-flops, we've got decoders, LEDs, multiplexers. We've got different shift registers here too. Counters, ring counters, latches, sequence adders. So we've got a lot more options. And again, keep in mind that we can make our own circuits as necessary in Falstead, at least in terms of what we can put in terms of other components. I'm not even really going to go over what's possible in QSpice because with a Spice simulator, you can literally bring in and import pretty much any component or model that you want. Obviously, the company that makes the simulator will probably have some of their products up as symbols, but other than that, yeah, you can pretty much do anything. Now, in terms of types of ICs, and this is definitely not an exhaustive list, you got voltage regulators, shift registers, buffers, transceivers, logic gates, op amps and comparators, latches, flip-flops, display drivers, counters, and then even CPUs, GPUs, NPUs, etc. They're all still ICs. And then memory chips, RAM, ROMs, PROMs, EPROMs, EPROMs, and again, microprocessors, microcontrollers, switches, timers, multiplexers, demultiplexers, and as I just said, this is not an exhaustive list. And just to give you an idea of prices, these are off DigiKey with ordering just one of each. Now, that's usually not the way to go, getting it directly from a wholesaler like DigiKey, but if you need a specific chip you can't get elsewhere, you actually might be able to find these for quite a bit cheaper, especially if you're buying, 5, 10, whatever off Amazon. Starting with a 74 series quad NAND gate, TTL Logic NAND gate chip. It says a buck 79. Again, I know you can get those for a lot cheaper. An NE 555 timer. That's just a classic timer IC, 51 cents. You got dual op amp here that we've mentioned previous, 87 cents. Uh, so you keep going, and even something like the Atmega 328P, which is used in the Arduino Uno Rev 3, is just 289. You can get a basic PIC controller for about 6, 7 bucks. Might be able to even find it cheaper than that. 595 shift register, 90 cents. Decade counter, 85. Darlington driver, 44. Even an ESP32 module for 8 bucks. So these are relatively cheap, but again, you have to understand scale of economy in this case. All right, now I did a little searching on Amazon to find a couple of IC assortment kits and to give you an idea what you might find in the one. The first one is very focused on audio amplifiers, so it's got a lot of amplifier ACs, ICs, comparators. It's got a 4047, which is a multi vibrator. You've got photocouplers; those are always useful. I'm not too familiar with the PTU 2399. It says it's an Echo audio processor. You've got some pulse width modulation controllers, some Darlington transistors, which have a lot of generic uses. You got a voltage converter. Interestingly enough, it comes with a 555 timer chip, and those just have a ton. Again, this is $20 USD. A lot of audio related chips, not as generalized. Second kit I looked at, it's about 16 USD. It's 20 models across 50 pieces, but actually 10 of those are dip sockets, which again, those might be useful if you get into soldering or whatever. You've got a bunch of logic chips, but they also have them in both HC and LS forms. And honestly, with very basic hobby electronics, the difference isn't going to mean much. But if it does, and then we've got a display driver, we've got a multiplexer, demultiplexer. We've got three different types of shift registers, the 595, but also the 164, the 165. More generalized, no amplifier chips, voltage regulators, etc. And they've really padded out the kit by including both HC and LS versions of the chips. But if you use those logic gates, then yeah, more power to you. You'll have more of them. All right, so let's break down some designations. There's general standards for these naming conventions, but there's always exceptions. Likewise, some parts of the designation may just mean stuff with the manufacturer. So let's take the 74HC595N, for example. 7400 series AC, cheaper commercial variant of the 5400 series. And yes, there's actually been other series, the 64 and the 8400 in industrial variants, but in hobby electronics, it's going to be pretty rare to actually find them. HC means high speed CMOS that got introduced in the early 80s, and the 52 and the 595 is a specific model. In this case, it's a 8-bit shift register with an 8-bit tri-state output. Again, we'll go over this in a later video. And N just refers to the fact that it has a plastic body. Let's try another example here. That's a CD4020BE. CD is a logic family that means CMOS digital. 4000 series introduced in 68 by RCA is their idea of a better alternative to the 7400 series. The 4020 model is a binary counter divider. B means buffered or improved CMOS, essentially enhanced output drive, I think is in the advertising. E is the packaging, which just means P-dip, much like in the previous example, met plastic. So we've mentioned HC and LS. HC is high-speed CMOS. LS is low-power Schottky. HC works with CMOS. LS works with TTL. HC is better and faster at higher speeds. While LS and TTL might perform better at lower speeds. LS is strict to 5 volts. HC can usually operate at 3.3 if it's needed. HC uses much lower power consumption, while LS is about medium power consumption. Both are really trivial, though. As I said, they're pretty trivial in a lot of these things if you're just using them for basic hobby electronics. The LS chip might have trouble with HC components in the same circuit, but again, lower speeds, trivial. HC means the inputs need to be more strictly controlled, such as not having floating inputs. LS is a little bit more tolerant to things like that. And then we have HCT, which is kind of a happy medium between the two that you might also see. All right, since a 595 often comes into a hobby kit, this is what we'll be discussing first is shift registers. It's a digital circuit made up of flip-flops, which we'll discuss in a later video, that store binary data and move it one bit at a time with a clock pulse. The 595 takes in serial data and shifts it out in parallel. So in this case, it would be 8 bits, although there are 4-bit registers out there. But it also has an option to cascade data via a serial data out. The main use for this is to have multiple 595s all linked together. It's defined as a SIPO, which is shift in, parallel out shift register. Uh, but it also has a second internal register, the storage register, which is what takes in the input. And then it moves it via a latch to the shift register. Not all SIPOs do this. It can be operated by hand, but it's normally operated with something with some more precision, like a microcontroller. Arduino has a whole library for dealing with shift registers, and once you understand the basic programming, it's actually not hard just to write out the commands by hand. You're basically just telling certain pins to turn on and off. The Pi, same idea, but there's so many ways to code with a Pi. Some of them may have good libraries, some of them may be non-existent libraries, but again, with the Arduino, once you understand that basic programming, it's really not all that hard. Shift registers are also specifically a digital IC because they work with zeros and ones, nothing in between, and the voltages are just creating references for 0 and 1 with logic levels, which we'll get into in a later video. All right, if you're curious how a 595 works here in Falstead, there's been one laid out. I didn't actually make this. I'm not really sure who did. I just found it on the internet. But this is how it works. You have your data up here, so high or low, whatever. So we set it to high, and then you've got the you got the latch right here, and you've got your clock all the way down here and your output. So we can turn it off or on. Now it's active low in this case, so we're keeping it low so it'll actually enable the output. Actually, let's set it for high for now. All right, we set it for that, and then we're going to do the clock. I think it's this clock. Yeah, yeah. Um, or not. Maybe it's the other one. Okay, that's 1 1. Let's set a low. So we've got 0 1 1 0 0 0 0 0. Okay. Oh yeah, I'm looking at the thing upside down. All right, so let's just say that this is the number we actually want in here. All right, let's move it to the actual register, and then we've got our output turned off, but now we have our. Oh yeah, here we go. Yeah, it's down here. So we've got our 0 1 1, which matches what we've had 0 0 0 0. So you're just using signals with these 5 signals to send data and move data. You even got your cascading one right over here. So let's set the high and keep moving things over. They, so we could have a second one over here if we wanted. Now, if you have a 595, keep in mind that the notch is at the top. So keep an eye out for that. Although with really small chips or bad eyesight, you may have to feel around. And each pin serves a particular purpose. So with a 595 in a PDIP package, this is what the pins would be. So I mentioned the outputs, and there's 8 of them. Um, and then you got ground, you've got VCC, you've got one of the outputs on the other side. Because in this case, they want a convention of VCC on one end and ground on another. You've got your serial input. You have the ability to turn on or off the output. Um, you've got a reset, which refreshes the entire chip. You've got your clock, and then you have your clear. Let's see, contain info. Yeah, yeah. The way they have these labels sometimes is a little weird. And then you've got your serial out for cascading. All right, we next have the 555 timer chip, sometimes called the 555, one of the most well-known chips, possibly the one you might get in a hobby kit. But don't let the name fool you. It has many applications. It has the usual VCC and ground, along with trigger, threshold, discharge, control, output, and reset. You usually use it with external components depending on the application you want. Often they are astable, monostable, or bistable modes. The internal capacitor discharges through the discharge pin and outputs a signal through the output pin. The control pin allows for setting different thresholds. The trigger is at 1/3 VCC and the threshold is at 2/3 VCC. Depending on your configuration, that means the output turns on at 1/3 of VCC and shuts off at 2/3 VCC. And of course, this is an example of an IC that is analog, as it deals with varying voltages across the range instead of discrete values. And here's the pinout that I mentioned. So you've got ground and VC on the top. You got trigger and discharge, output and threshold, reset and control. All right, we're on every circuit with the 555. So yeah, we've got a VCC of 5 volts. Resist is being tied to VCC because it's active low. So if we took this off and moved to actually since everything's together, it would do more than that. But um, we've got 2 resistors. The ratio changes the pulse. On the output, we've even got a faint LED. So basically, using this external capacitor, it's charging up, then it's discharging. So let me pause it. So when it gets down to 1/3, it turns on the output, and when it gets up to 2/3, it turns it off. And then this is not at 5 volts because of the nature of the circuit, but you get the idea. It's actually going against the 5 volts here, 1/3 to 2/3, not the output pulse. And then we have nothing connected to the control pin. I'm not really concerned about noise with this because everything's so simple, but if I really cared, I would put a little capacitor right here. And actually, it doesn't even need to be much, like 100 nanofarads. I don't think it's going to have much of an effect on this circuit. It's best practice and all that. So let's start it up again. Now that this first pulse is fat because everything's starting up. In real life, it wouldn't immediately start blinking. It takes it like a second. Um, and in terms of speed, if this is no, actually, maybe this might. This is set correctly, and it might not be. I think it's 1.02, but I have to do the math. All right, we're going to look at Falstead, and it's essentially doing what it did in every circuit, but you can actually see the internals of a 555, see the discharge, trigger, threshold. It's not the exact same numbers, though, because I don't really want to mess with the internals, but this gives you an idea. So there's not a whole, in the actual chip, these things are all, it's all transistors. And then looking in QSpice, here's a schematic. Now, they're all moved around a little bit differently than the other schematics. Certainly don't match the pin, but that's fine. So this is more set up like every circuit is. So let's run it and see what we get. All right, so you see that fat pulse in the beginning there, so ignore it. But yeah, you've got your output pulse to 5 volts. I'm not dealing with that whole LED business. And then you've got your, I guess, red or green is the capacitor. It goes to 1/3, it turns on, it gets to 2/3, it turns off, it drops out, it charges again, 1/3, 2/3, and so on. All right, let's move on to multiplexers and demultiplexers. They're a combination logic circuit that allows one of several inputs to be selected for a single output. Kind of think a rotary dial where different modes can be selected with for a shared output. The opposite is true for demultiplexers, where it's one output into multiple inputs. The largest ratio between the two is usually it's 16 to 1, although apparently there's examples of 32 to 1. Although after that, you're using other technologies that have their roots in multiplexing. And here for a table, you probably didn't ask for how many select lines do you need for a given number of inputs or outputs. Um, and again, for two to one, and so on. Usually, I think the lowest I've seen, no, I have seen 2 to 1, usually multiple on the same chip, but 3 to 1, 4 to 1, whatever. And again, if you go to 16, you need 4 select lines. If you go to 32, you need 5. Here's a pinout example for the 74. It could be LS or HC, I think. 151. You've got let's see, you've got input line. You got four. No, you've got 8 input lines on this one, and you get 1 output. They have a complementary output too, so the reverse, and there's an enable line, and then there's 3 address lines right over here. All right, now we're going to go into every circuit here. I built a basic 2-channel multiplexer. So we actually don't even, well, we have a select line right here. So our select line is actually the middle here. The bottom is a 0, the top is the 1. All right, so it's currently selected to 0, so whatever comes here will affect the output. Change the other one, and it doesn't do a thing. And we change this to the other one, and now it decides, and the other one does nothing. All right, let's take a look. Multiplexers, demultiplexers, and Falstad, which we've got other options. All right, so this is just a simple 2 to 1, kind of like what I did in every circuit, but we're using MOSFETs here. Set 1 to high. So this is the one. Set it to the other one. This is not doing a thing. So yeah, we're using logic gates and MOSFETs for a tri-state buffer here. All right, let's look what our options are here. We got multiplexer, demultiplexer, and we've got an analog multiplexer here. Mind you that even with the analog one, the select lines are still digital, and these are pretty simple. These are 4 to 1, all 4 to 1s. Although you actually, oh no, yeah, you can select. Let's see, you can change high logic voltage, number of select bits. I wonder if that actually changes. Yeah, no, it does. Okay, so it does it automatically. All right, that's good to know. All right, so with the fully digital one, it's going to be whatever is on 0. Now, if we change this, well, actually, let's just flip them to, okay. So going to the next one, you'll see. All right, and then number 2, okay. For number 4, there we go. So pretty simple. Demultiplexer is basically the same idea. Um, so our output 0, and then where we want to put the basically where we want to put the input. And then the analog here is the same, except we can actually input analog voltages, although the selection, as I said, it was the same. So we got 0, we got 4, we got 3, do it both, we got 2. All right, we're moving on to encoders and decoders, which are related to the mux and demux we just talked about. I don't really want to keep saying uh, multiplexer and demultiplexer, so usually they're called mux or demux. An encoder takes a larger number of inputs, encodes them into a smaller number of outputs. The decoder does the rest. It takes a smaller number of inputs to output a larger number of outputs. An example of this is the 74LS147, which takes a decimal number between 0 and 9 and converts it into 4-bit BCD, or it can be configured to convert a decimal number between 0 and 7 and convert it into 3-bit binary value, which it effectively becomes an octal encoder, and we'll be discussing all of this in a later video. The big difference between encoders and decoders, generally speaking, is they're sending information, while multiplexers and demultiplexers are essentially just routing signals. Now here's a correct pinout for the 74HC147, and it's not going to matter whether it's HC, LC, HCT, that should all have the same pinout. Unfortunately, some of the pinouts are missing the fifth input line, and we're calling that non-connected. I think that propagated from one particular website who otherwise has great graphics, but I digress. So 1, 2, 3, 4, 5, 6, 7, 8, that's the input. A, B, C, D, that's the output. We've got one non-connected pin, assuming this is not an error, VCC, and ground. All right, so let's look at some encoder here on every circuit. So basically, yeah, the position of these bits is going to determine this is not actually a binary number. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, here's another one. I'm trying to keep the page up so you see the name and the name of the person who made it. So yeah, we're starting at 1, 2, 3, 4, 5, 6. Yeah, okay, we're right. 6, and then finally 7. And of course, 0 is obviously 0. All right, I picked up Simu IDE, which I haven't had up in a while, just to show off one of the ICs. This is the 74HC42. And basically, the light will go off corresponding to the decimal digit that's presented here in 4-bit value. So right now, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we're at 0 because nothing's here. Press 1, we're at 1. 2, we're at 2. Now we're at 3. Now we're at 4, 5, 6, 7, then 8, 9. If we do anything more, it's just no value. All right, we've talked about encoders, decoders, so let's talk about a specific type of decoder, which I've left to its own section, and that's a segment decoder. It simply decodes a binary or BCD number to the correct set of 7 lines that make up the display, so the user doesn't have to keep setting individual lines anytime they want to display a number. Keep in mind this is extremely important. The decoder really should match the 7-segment display, common anode or common cathode, although there are ways to simply invert this with an inverter chip, for example. Although the largest one I know is hex, so that's one shy. So you need 2 chips most likely. A single digit is going to display 0 to 9. but 4 bits count from 0 to 15. So the other values may just display garbage, a certain symbol, or nothing at all. This is purely because of the chip and not the display itself. The display itself, you could do A, B, C, D, E, F, hex display, but if the chip doesn't do that, then you're not going to get those values. Specific ICs probably also have a few more features like lamp testing, zero suppression, which is where it blinks on a zero, blanks on a zero, cascading blanking between digits, and maybe some other features. Here's an example of a 7-segment decoder. It's the CD4511. Um, you've got your 4 input bits here. You've got a lamp test so that when it's active low, so you need to keep this to high. And then this is the blanking, I believe. Um, So you need to keep this high, and then LE, I can't remember off the top of my head. We've got voltage, we've got ground, um, and then we've got our 7 segments here. So the LE is a latch, whether or not you change the digit or you freeze it. Um, this could have a lot of uses, and this is set up for a common cathode. So you'll want to display a digit that is common cathode as well. Then again, you can do some inverting if you need to, but the chips are cheap enough. Now let's look in every circuit here what we can do. Now we don't have access to a specific chip, but we do have, let's see, there we go. All right, this is really simple, just 7 segments. Let's get out a segment display, whatever it is on the list here. Here we go. So yeah, in this case, it's pretty easy. Just connect A to A, B to B, C to C, D to D, E to E, F to F, G to H. Now, I don't think we can really, let's see, wavelength, voltage, current resistance. Okay, so we really can't set common anode and cathode. As far as I know, actually, this will work regardless. Let's just see what happens before we hook up a number. Okay, it's a 0. We don't have the zero suppression feature. But regardless of what this other thing is, actually, I think, come to think of it, I think this might be the decimal point. One way we can figure that out too. Oh, actually, you know what? Just keep this simple. Let is just do logic sources. Let's put a logic source to the other thing as well. All right, let's run it. All right. Yep, it's just a decimal point. In this case, I'm not sure. Well, you could probably do something with it. Um, but yeah, 1, 2, 4, 8. So that would be 2. That would be 3. Go to 4. Go to 5, 6, 7, 8, 9. Now with this, it actually will display hexadecimal digits. Keep in mind, that's not always how it works in real life. Unless it actually says it does that, then don't assume anything. Now here we're going to look at Falstad. Same basic idea as in every circuit, just a little easier to move stuff around though. Uh, and the G, let's see, 8. Okay, yeah, that does use everything. You'll want to actually make sure all the lines are set. Go with an 8 because it uses all the segments. See if there's any support for anything else. 7, 14, 15. Extra segment for colon or decimal point. Diode. So we can actually set this to common anode or cathode. Get it a little closer. Now the actual chip, different segments, blank pin, blank on 111. Okay, so we got some options. And again, since we could do subcircuits, we could technically build an entire chip and use it in fall stud. All right, now we're going back to Simulute IDE, and we've got a setup with the CD 4511 that we mentioned earlier. We've got a battery, we've got switches. Now there's some important things here. Lamp test, that'll just display an 8 to show everything. Actually, you know what, I really should have this lower. All right, because in real life you're going to want a resistor or you will blow the display up just like any other LED. And this is a common cathode. We have nothing attached to the decimal point. So that's the test. So it's going to be active low, so we need to keep it high. And then BL is whether or not we want to blank it. So we'll turn it on. Okay, 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. See what happens when we go higher. Nothing. Just like the actual chip. Although the actual chip and the actual case, you might get garbage. I'm not entirely sure. Okay, so 0. Put it on 1. Let's turn on the latch. Let's see what happens. See, the number still stays the same. Now we're moving on to counters. And it's an IC that counts in some systems such as binary, BCD, hexadecimal, or even just plain decimal. While the specifics of each AC can vary wildly quick. So basically, you have asynchronous or ripple counters, synchronous counters, decade or decimal counters, Johnson counters or modified ring counters, and then ring counters, either straight or twisted, and there's possibly others. One example that I've used is the 74LS90. This can be wired as a three-stage binary counter, which is also known as a divide by 5 counter, a divide by 2 counter, or a divide by 10 counter, which outputs either BCD or biquinary. All right, here's the pinout for the 74LS90. It has 2 clocks. It has a not connected, um, and it has the outputs and inputs along with VCC and ground. All right, here we're on every circuit, and what we've done is we took what we did earlier with a 7-segment decoder, and we've now added a counter. So this counter here is not completely representative of any real life IC, or at least as far as I know. So we've got an up and we've got a down. On the rising edge, it will, and we can attach this to a clock signal, and we'll get into that in a later video. But yep, we can keep counting and keep in mind the chip outputs A, B, C, D, whatever. Let's reset it. Now the digits on the left, most people don't realize what they actually do. They work with the load. So if you want to start a value 1, 2, 4, or 8, you pick 8, immediately load that in. Now this doesn't add or anything. This just loads this particular value. I don't think. Yeah, no. Okay, it will add if you have them both go high at the same time. So C is 12. We've also got carry and borrow, but we're not going to mess with that for now. That's good for cascading multiple counters together. But let's take a look at making this a clock, actually, just so it's automated. Now, I guess technically this counter in a weird way could be sort of used. I think maybe like, well, not technically a decoder, I guess, but you could feed in a 4-bit binary value to where you get it started to load it in. And then it would go to the segment. All right, here in Falstad, we basically have what we just had in every circuit. We've got a really simplified counter here, and basically this is for our clock pulse, but we're manually doing it. So we're just having to hit one thing now to just count. And we've got a reset line there as well. There's no up or down with this counter. So let's look at the other counter that's on here. Counter with a load, and there's a ring counter. Oh, oops. And then the counter with load has basically what the other two have. The other one, I mean, from every circuit. So let's set bits, modulus. You got clear and load, and I think works the same. Let me just double check. All right, we have our setup here with every circuit with the this particular counter, and that's what is it called again? Counter with load. So this is really close to the 161 or 163 chip. It's not indicating what's actually supposed to be active low or high. That's a problem. These two at the bottom have to be set to high, the ENP, ENT, and then the load mechanism. Um, Actually, if I set it to high, I believe it does nothing. Yep, okay. And clear is apparently active low, and then these are active low too, and then the load behavior I think is active low. So these should all actually have a bar over them. Anyways, it's connected. This is a ripple counter for moving, cascading the chip. So yeah, we're just clock pulsing it, and it goes up. And if we set the load to low, and we'll set it for the last digit, so it'll start with an 8. This will be a 4. Yep. All right, let's move on to SIMU IDE. We've got a 74 LS90 hooked to a 74 LS46, so we've got two chips working together here as a counter. So let's take a look on how this works. Actually, let me turn everything off before I. So it's in lamp test mode for the 46. So let's take it off that. It's blanked. Now, if we want to see a 0 when it's 0, or we want it to be blank, this is our BI/RBO button right here. And then this setting either switch is going to show 0. This is, I think, ripple blank. Both of them apparently will show a 0, but they do have other functions. This is ripple blanking in, ripple blanking out. I'm not entirely sure. Um, I haven't used some of the functions of this, so all right, since it's running, let's take it off, reset. If both of these are high on the 90, it will simply reset. Okay, let's turn on the clock, see what happens. All right, let's reset it. And the lamp test is just going to show 8, but it's still counting, I think. Yep, it's still counting. All right, now for the last type we're going to cover are logic gate ICs. Often enough, they'll actually have several independent copies of that same logic, 2, 4, or even 8, with a shared power and ground. They may take in or output Schmidt trigger signals. We'll get to that later in a later video. At the very least, it introduces a delay since it has to process that data. It's known as a propagation delay. It's usually measured in nanoseconds. This could be a serious consideration when you're dealing with high-speed operations. Um, Now, we could also take multiple gates and chain them together for our desired effect. Like you could take a quad two input NAND IC and chain it together just within that one for a five input NAND gate, simply feeding the output of one gate to another. Another example of a logic gate IC is the 74LS32N. Keep in mind, it could also be HC instead of LC or HCT or whatever. And the N just refers to plastic body. It's a quad two input positive OR gate that gives you four separate two input OR gates. Keep in mind that positive really just means regular OR, and they share a VCC and a ground. All right, here's the pin layout for the 74LS32N that we just described. You'll see 1A, 1B, and then 1Y. So A or B equal Y. And then you've got a second set here, a third set here, and a fourth set here. You've got your shared VCC and ground. All right, now I can't produce the IC for logic gates in every circuit, but I can show you sort of with logic symbols how the five uh, input OR gate I was talking about might work. So you've got all these, and the light will light up if any of these conditions are true because this is an OR gate. So that lights up, that lights up. It's not going to matter if they're all lit up. As long as one of these is true. All right, here in Falstad, here we've got the same five input logic gate. We turn on any one, and the light will blink, will light up. Multiple is not going to matter because it's an OR gate. Lastly, we're going into SIMU-IED, and this is the exact chip I was already discussing, 74. This is HC32 version. We've got our, since this is a nice little schematic, as opposed to the actual pinout, we've got our 1A and 1B all the way to the 4A and 4B together. All right, nothing. And now these aren't chained together. These are four independent gates. So first one, turn on, second one, third one. Now, I could in this simulator actually chain them together if I want, but I don't think you need to see a third example. Now, just to wrap things up, an IC is short for integrated circuit, and sometimes we just commonly call this a microchip. That term has been in existence since I think at least the 1960s. It's an entire circuit fabricated together in a single package. Components are microscopic, allowing anywhere from as few as a few dozen components to billions of them in a single package. In fact, a modern CPU is about 100 billion. There's many types of ICs, and they use different logic families in their implementation. There are many considerations to choosing an IC, really just starting with what do you need the IC to do. ICs can also come in different packages, and not all are suited for use with a breadboard. Look for DIP or PDIP in that case. ICs can be analog, digital, or a mixture of the two, really. If you're dealing with bits, you're dealing with digital. Analog is varying voltages or currents. Keep in mind, we also saw chips that were dealing with analog inputs and outputs, but the select lines were digital. We discussed shift registers, timers, multiplexers, demultiplexers, encoders, decoders, specific 7-segment decoders, counters, and logic gates. With logic gate ICs, you often have multiple of the same logic gate on the same chip. Well, until next time, have a good one.